Our first presenter will be Dr. Iadecola, Konstantina Iadecola, who's been a major contributor right from the beginning on the concept of the neurovascular unit and neurovascular coupling, and his talk is appropriately entitled The Neurovascular Unit, Neurovascular Coupling in Health and Disease.
Thank you. I thought I would come on the podium early so he wouldn't give my talk. The way he was going, it was almost like headed that way. Anyway, thank you very much. Thank you, Marie-Germaine, for giving us this opportunity. And today I'm going to tell you a little bit about the concept of neurovascular unit and one of the functions of the neurovascular unit, which is so-called neurovascular coupling, and giving you a very kind of 30,000 feet view of the problem, just to set up perhaps the contributions of my colleagues will be much more detailed than mine at that level. But then I'll talk about a little bit more about what happens when the neurovascular unit gets damaged or somehow becomes dysfunctional, and how that may contribute to a number of situations in the brain that lead to cognitive impairment. Now, I think one of the major contributions that the CADASIL field that was established by Marie-Germaine is that give us proof that when the vessels of the brain do not work, cognition doesn't work either. That's been extremely important for us because it demonstrates what we knew all along, all right? But we couldn't prove that essentially vascular health is fundamental to cognitive health. And all the conditions that lead to cognitive dysfunction have a contribution on neurovascular dysfunction. And that's going to be the take-home message, I guess, and I'm going to use a bunch of slides to show you that. So the brain is uniquely dependent on a constant and well-regulated amount of blood flow, which provides oxygen and glucose. And this amount of blood flow has got to be just right. It's got to be delivered, with temporal and spatial precision, which is an enormous problem in the brain because you have billions of neurons grouped in different ways, each doing what they want to do. And each one needs to be supplied at the time and at the place where it needs to be supplied, which is a logistical nightmare, if you think about it. So this is achieved by this concept of neurovascular coupling or functional hyperemia, whereby active neurons tell the blood vessel they need more blood. Now, the telling is a little bit complicated, right? But this is very important for a number of reasons. Perhaps can you lower the lights a little bit? One of the big ones is that, functional imaging is based upon neurovascular coupling, and that's the secret of the people who do MRI do not say. So essentially, you're looking at a hemodynamic response generated by neural activity. You're not looking directly at neural activity. And that's been kind of pioneering work of Ingvar and Lassen, who really established, building on the work of Seymour Cady and Lou Sokoloff, really established this concept as shown in this Scientific American cover in 1978. Now, another big one is the autoregulation, which we heard in different shapes and forms yesterday, which is the ability, which the brain does not shares with other organs. It's not the only organs who's got autoregulation. And is based upon the ability to maintain blood flow relatively constant despite changes in arterial pressure within a certain range. So if this is cerebral blood flow, this is arterial pressure, between let's say 60 and 120 mean arterial pressure, flow does not really change. And this is very important for the brain because it gives it a buffer isolating the cerebral circulation from changes in arterial pressure, which, as you know, are the force that pushes the blood through the vessels. So the more blood pressure you have, the more flow you would have, unless you have a myogenic response that we heard yesterday, which is the ability of the smooth muscle cells to constrict when intravascular pressure increases, thereby increasing resistance and keeping blood flow constant. Why do we need this? Well, we need this because our blood pressure changes by 50, 60 millimeters of mercury, depending on what we're doing. So if you're asleep, your blood pressure may dip, as they say, to 80, 60 mean, or even systolic and so on. If you're doing exercise, isometric exercise, you have 200, 250. So the brain cannot rely on such a wide, changes in blood pressure. So you need a base on which then all these alterations that induced by functional hyperemia and so on can be superimposed, as opposed to have this kind of fluctuating baseline, all right? And then you have the vessels themselves, which are extremely intelligent, tubes. They have a lining, which is called endothelial cells. And then there is a business end, which is a contractile apparatus that kind of constricts the vessels or dilates the vessel, allowing more or less blood to go through, pretty much like in a conductor for electricity. The larger the conductor, the more blood flow, and current goes through, so does the blood vessel. So if the vessel constricts, the resistance to flow increases and the flow slows down. If the vessel relaxes, then there is more flow going through, and there is a drop in resistance, and the flow goes up. Now, endothelial cells are very smart cells that transduce chemical and mechanical signals to which they are exposed from the flowing blood that pulls on the cell membrane, creating what's called shear stress. And this shear stress is a mechanical force which, through very complex apparatus, is converted into a biochemical signal, which is, for example, nitric oxide, that is being released to adjust vascular diameter. So all these things work together in a very amazing, beautiful harmony, and allow this neurovascular coupling business to occur. And thank God for that, because if this wouldn't happen, as you will see, there will be a problem, major problem. Now, as Mike Moskowitz said, at the beginning, the idea was that, Roy and Sheridan really took the idea of Roy and Brown, which worked on the skin of the frog, saying that, when you activate cells, you release some vasoactive agents, and they thought it was hydrogen ions that then would diffuse to the blood vessels, producing the vasodilation. Turns out that things are more complicated, as Mike intimated, and now we know that this is a very complex phenomenon, which, although is triggered by neural activity, so synaptic activity is still the factors that initiate the cascade. The implementation of that signal is complicated and is mediated by all the cells that are part of the blood vessels, each one playing a very defined role to transduce a signal saying, I want more blood flow, to an effective hemodynamic response that, as you will see, involves multiple cells, involves multiple segments of the cerebral circulation in a very complex arrangement. And so the same phenomena occurring postsynaptically that lead to an increase in vasoactive mediators like adenosine, COX metabolites, and nitric oxide synthase releasing NO also occur in glia, and then the ions converge on the smooth muscle cells. Endothelial cells play the role as all this happens, to kind of stabilize the flow, and the whole thing works, as I said, harmoniously, and results in this highly precise and temporally defined increases in blood flow, which we see after neural activity. Complicating the situation is the fact that the brain is vascularized from the outside in, unlike other organs, like the liver or the kidney. Now, what the problem with that is that while the action, neurons' activity and all of that occurs in the depth of the cerebral, let's say in the cortex, the major controller of blood flow to this region is really up here, is the PL vessel that dilates during a neural activity. All right? So the question is, how does the signal generated down here gets all the way up here to mediate these very accurate changes in blood flow? And how come that when you do that, you don't increase blood flow in nearby areas which are also supplied by that vessel? So that's a very complex problem. And now, thanks to work in the peripheral circulation, we're gaining a little bit of an insight of that may happen. So what people think that may happen is that there is all this complicated neurovascular coupling business, occurring at the level of the arterioles and capillaries. And then there is a system that conveys this signal all the way up to the larger arterioles, probably through a process of retrograde vasodilation, flow-mediated vasodilation. There's a number of names of these things, but essentially cell-to-cell communication through ions and through perhaps nitric oxide that kind of retrogradely transmits the signal until you have a dilation of the business end of the arterioles, which is up here, leading to an increase in flow, which then reflects, kind of satisfies whatever is going on down here, all right? And this is really this kind of retrograde vasodilation phenomenon that I think is the best demonstration of the working of the so-called neurovascular unit. So we're not talking about capillaries, we're talking about capillaries, arterioles, venules, and arteries working together harmoniously to produce this hemodynamic response, which is, has this amazing temporal and spatial laminar precision. In the cortex, you can see increases in flow in laminar 4. And don't ask me how that takes place. It's very complicated to do so. However, the neurovascular unit does not just do the blood flow control. It does a lot of other things, which, thank God, now they are kind of drifting into our common, clinical problems, because we are discovering that there are other things that these vessels do. So, for example, blood-brain barrier exchange, which is a major function of the vasculature of the brain. So nothing gets into the brain unless the endothelial cell wants to, unless it's cocaine or heroin. So it's a very lipophilic substance that gets through the endothelium without asking questions. But everything else that matters, like, for example, glucose, vitamins, essential amino acids, and ions and so on, they got to be carried from one end to through the endothelial cell and then get into the brain. That occurs mainly at the capillary level, where the action is for the exchange. Furthermore, the same process occurs the other way around. So the brain makes a bunch of stuff that the brain doesn't want. I'll give you an example. Amyloid beta, is made when I'm talking to you now. I'm making a lot of amyloid because synaptic activity generates amyloid, all right? A beta, the peptide. Now that peptide has got to be gotten rid of, because if you don't, you know what happens, all right? And so how does that happen? It happens through the blood vessels. And there is a very specific transport process mediated through LRP1 that Mike is already looking at the watch. That allows this process to occur, but I need to move forward. So immune surveillance is another important function. Monocytes traffic back and forth through the endothelium. So lymphocytes tracking back and forth, and they patrol the brain. And also, the new concept that is really emerged is the trophic support that these cells are into it. So, for example, neurons make vascular growth factors. Go figure, all right? And endothelial cells make neuronal growth factors like BDNF, all right? And what does that mean? That means that if a neuron dies because there is a primary problem with the neuron, all right, like in ALS, for example, the vessel is also going to die because it lacks that trophic support provided by the neuron that is dead. The other way around, okay? If you have a vascular damage, the endothelial cell is not going to make the growth factors, NGF or BDNF, and so the neurons cannot survive. So that's really this trophic, interdependence that these cells are. And this clarifies a number of issues that we face with neurodegenerative diseases and with vascular disease of the brain. This inextricable, interaction between vasculature and brain cells and so on. So that we got to pay attention to. However, all the major factors affecting cognition have a profound effect on this neurovascular coupling. And I'm going to give you now an example, drawing on some of the work we've done in Alzheimer's models that exemplifies this approach. Why does, oh. Okay, so as you know, Alzheimer's disease, one of the major hypotheses right now, we believe is that there is an overproduction of a peptide called amyloid beta peptide, which is produced by cleavage of a larger protein called amyloid precursor protein by proteases called secretases. So the two main species of A beta are A beta 1 to 40, 1 to 42. 1 to 42 is very sticky, so they stick together. It forms oligomers, lower and older aggregates, and then ends up accumulating in the brain to form amyloid plaques, which is the pathological hallmark of Alzheimer's disease. 1 to 40 instead is less sticky, so can travel to the tissue and finds its way to the perivascular space, where it accumulates around blood vessels to form vascular amyloid. So these are the two major manifestations of the amyloid accumulation in the brain, which have been thought to cause the disease predominantly by affecting neuronal dysfunction. Neural function. For example, we know that oligomers of A beta can block synaptic transmission, can alter synaptic communication. That's thought to be at the basis of the dementia. You do not need the plaques to get the dementia. All you need is A beta that affects synaptic. And that's very become very obvious now with the recent data that Bateman and his colleagues provided. So, however, there has been always around the idea that A-beta may also act on blood vessels, producing vascular dysfunction, which then in turn compounds the deficits of neuronal activity. And that's what we've been doing for a number of years, using a model of neurovascular coupling that is based upon the fact that the whiskers, the facial hair of the mouse, are very important for the mouse life. It's like a sixth sense for the mouse. And there is a lot of real estate in the brain devoted to regulating this whisker business. Okay, so if you stimulate the whiskers mechanically, just by moving them side to side, you can generate field potentials in the somatosensory cortex and increase blood flow in the activated area. That's a very ideal model to study what's called neurovascular coupling, because there is no question that what drives the response is really the brain, all right? So blood pressure doesn't change, as shown here, nothing else changes. So this is an anesthetized mice in which a cranial window is placed, blood flow is monitored at the site of the activation, and then you can even throw stuff on the brain and test other things. For example, if you put acetylcholine on the brain, you study endothelium-dependent relaxation, which is mediated by nitric oxide. If you put adenosine on the brain, you study smooth muscle relaxation, which is mediated by the smooth muscle, through a cyclic AMP response. So we use this model in an Alzheimer mouse model, which was introduced by Karen Shao in the early 90s. So we've studied these mice. We asked the question, when can we see this alteration in the brain of these mice? What is the earliest alteration in brain function we can detect in these mice? So we looked at at mice when they were teenagers, when they were 3 months old, which is a teenager mouse, and we looked at the vascular regulatory effects. And what we found, to our surprise, was that the cerebral circulation was completely screwed up. Nothing worked. Endothelium vascular responses were attenuated. The neurovascular coupling was attenuated. Cerebrovascular autoregulation was non-existent. So these mice really were at the mercy of blood pressure, essentially. Now, and this raised the possibility that, and this was mediated by beta amyloid, by the way, A-beta. But before it accumulates to form the plaques, all right, it's still the peptide floating around before it aggregates, because at 3 months there is no evidence of any plaques. Then we went on and asked the question whether this may lead to an increased susceptibility to ischemia. Because after ischemia, as you know, when you occlude an artery in the brain, there is something called collateral circulation. So there is blood coming from nearby territories which are normally perfused that goes to the help of the territory which has been rendered ischemic, all right? This collateral circulation depends upon the health of the blood vessel. We hypothesized that because in these mice, the vessels did not work correctly, the collateral circulation was not happening. And that's what happened here, is shown that there was when you occlude the middle cerebral artery, at this point, you have a drop in blood flow, which is much greater in the mouse that overexpresses amyloid. It stays down there. And then, whereas in a normal mouse, there is a recovery. And this results in an increase in infarct volume, suggesting that if you have A-beta in your brain, you may have an increased incidence of strokes. Now, is that true in patients? The answer is yes. So Kurt Jellinger, which is one of the most famous neuropathologists working in Alzheimer, he took 1,000 brains from a bunch of patients with Alzheimer's disease and controls, and he looked at the cerebrovascular diseases, quantified them from 0, nothing, no cerebrovascular disease, to 3+, which is a lot of cerebrovascular disease. And he looked at the proportion of patients with and without Alzheimer who had vascular lesions. And he found that in people who have no vascular lesions, there were more controls, whereas in people who had lots of vascular lesions, there were more Alzheimer patients, suggesting the incidence of strokes was increased. Those 2 studies just recently published in Neurology confirmed that. These epidemiological studies look at the incidence of stroke in Alzheimer's disease, and they both found that there was an increased incidence, both a community-based study and a register-based study. So it seems like having Alzheimer increases your propensity to have strokes, like we saw in the mice. Now, what mediates all these changes in blood flow and so on? Well, it's really oxidative stress. As shown here, using 3-nitrotyrosine as a marker, you can see endothelial oxidative stress and also in the adventitia of the vessel. What makes the free radicals? is an enzyme that Frank Ferresi mentioned yesterday. It's called an ADPH oxidase, initially described in neutrophils, responsible for the respiratory burst of neutrophils. Neutrophils kill bacteria by releasing free radicals. And when they do so, they use oxygen. That's why it's called respiratory burst. All right? So this enzyme was discovered in every single cell in the body, neurons, endothelial cells, smooth muscle cells, and we have evidence that this contributes to the vascular dysfunction. How do we get to that point? We crossed mice overexpressing the amyloid precursor protein with knockout mice lacking one of the isoforms of an ADPH oxidase. By doing so, through a complex breeding strategy, which is shown simplified here, we found that you can generate mice who have the transgene but do not have NOX2. And we would anticipate these mice would be rescued, would be perfectly normal. And that's exactly what happened. So when we did so, the blood flow response to whisker stimulation was completely normal, and the cognitive function of the mice tested at the Y maze also became completely normal, and the free radical production was suppressed. So if you get rid of NOX2 in these mice, you suppress free radical production, the vessels work better, and you do not have cognitive dysfunction. So go figure. Now, how does A beta activate an ADPH oxidase? Right? A beta floats around in the extracellular space. How does it get to an ADPH oxidase, which is an intracellular enzyme? Well, it's through a scavenger receptor called CD36, which is a major innate immunity receptor present in monocytes and endothelial cells as well, that is able to induce inflammation by producing cytokines through NF-κB activation, as well as oxidative stress through an ADPH oxidase activation. And as here we did the same experiment. We crossed transgenic mice overexpressing the amyloid precursor protein with the CD36 knockout mice. And the crosses, this group here, had reduced radical production and had a perfect vascular regulation. So if we can, CD36, which is upstream of an ADPH oxidase, all right, is able to completely rescue the alteration. Now, when we looked at the aged mice and we looked in greater detail, we found something extremely interesting. That by if you knock down CD36, you reduce amyloid that accumulates in the blood vessels. And this was the first time this was found. So you have a kind of a mediator for cerebral amyloid angiopathy. So here, this is thioflavin S stain, which is a stain for amyloid and actin counter stain. You can see there's much less thioflavin S in the vessels. And also, we found that the number of plaques instead, by counting them one by one, these little things here, was not any different between the two. So it looks like if you remove CD36, you selectively make the vessel accumulate less amyloid beta. And the smooth muscle cells, shown here with an actin stain, are less fragmented. So this is a fragmented smooth muscle cell. These are the number of fragmentations. And this is the fragmentations in the mouse that lack CD36. So you're able to make the blood vessels much better with respect to smooth muscle cell. Then there is pericytes, which are very susceptible to A beta, and David Atwell will talk about that. They are also remarkably rescued by eliminating CD36 in these mice. And here you can see an abnormal pericyte, which is hypertrophic. It's got long processes. That is shown by EM, that is completely rescued by eliminating CD36. So both the structure of the blood vessel and the function of the blood vessels is improved by removing the scavenger receptors that binds A beta. Now, next question is, what are the cells where the action is? CD36 knockout was removed, from all cells. So can we get better cellular specificity of what's happening? Well, one idea was that A beta is produced in the brain parenchyma, and then is drained from the perivascular space into the cervical lymph nodes in what's called a pseudo-lymphatic draining system that has been recently emphasized, but it's been known for a number of years. So we hypothesize that perivascular macrophages, which are monocytes that come from the blood and then kind of set residence around the blood vessel, are involved in this process because they have loads of an ADPH oxidase, and they also have the receptor for A beta CD36. Now, how do you study the perivascular macrophages? Here I can show you some of them. CD206 is a specific marker, so these are the macrophages around the blood vessel. GLUT1 is an endothelial marker. Now, to kind of modulate the perivascular macrophage, you can do bone marrow transplant. Because when you do bone marrow transplant, these monocytes, get into the brain and replace the one which were there before. How do we know that? Well, if you transplant a bone marrow which is fluorescent, okay, a GFP positive bone marrow, you can then look at the new perivascular macrophages and see if they're the old one or the new one, all right? And that's what we did here. So we transplanted GFP positive bone marrow, and you can see the perivascular macrophage, 80% of them, both by histology and by flow cytometry, were essentially replaced. So what happened if we transplant CD36 negative marrow into a mouse that expresses the amyloid precursor protein? So as you by now may have inferred, if you do so, by transplanting it, you can completely rescue the vascular dysfunction. So it looks like, these perivascular macrophages are an important constituent, may not be the only one, all right, but are critical. Last question is, what is how do the radicals screw up vascular regulation, all right? So we found that to do that, these radicals need to make peroxynitrite, need to damage DNA, activate PARP, then through this enzyme that decomposes the poly-ADP ribose in single ADP ribose, activate a channel in endothelial cells called TRP2 channel, TRPM2 channel, leading to entry of calcium and endothelial dysfunction. And you can see here what's going on. You can have, if you add A beta to endothelial cells in cultures, you have DNA damage, activation of PARP, and production of PAR. And all of this that is shown that is all peroxynitrite dependent, PARP dependent, and PAR dependent. The activation of this, of the production of this PARP then leads to currents in the endothelial cells which resemble TRPM2 kernels by IV curves. And you can see that this current is blocked by 2-APB, which is a blocker of the TRPM2 channel. So it looks like A beta opens up this channel leading to these changes, and these currents are dependent upon PARP activity because it can be blocked by PGA34, and PARG activity because it can be blocked by this blocker. A beta increases the calcium in endothelial cells, as I showed you, and attenuates NO production, which is also reversed completely by blocking this channel. So it looks like, this is kind of quickly, that the same thing occurs in vivo. All right? So if you have A beta in vivo, makes peroxynitrite, which is this stuff over here, and it causes endothelial dysfunction, which is completely rescuable if you inhibit PARP, or if you block peroxynitrite. Then PARP activity, if you block it using PGA34, you can rescue the dysfunction. A beta does not work in a PARP knockout mouse, all right, because you need PARP activity. And the inhibiting PARP rescues the vascular regulation in the transgenic mouse. And 2-APB, which is the inhibitor of the TRP2 channel, also rescues the dysfunction. So the data then suggests that there is this peroxynitrite, which can come from the endothelial cells, but can also come from outside, because peroxynitrite is very cell membrane permeable. So it can come from the perivascular macrophage or other elements around the blood vessel and activate DNA damage, leading to that chain of event that I just described for the endothelial cells. Now, is this relevant to human Alzheimer's disease? So is there evidence that controlling vascular risk factors, or making the blood vessel work better, is going to work also in Alzheimer's disease? Well, there is some evidence. This is shown by a study done in Lille, in which they took a bunch of patients with Alzheimer's disease, and they divide them into 3 groups. Some patients had perfect control of vascular risk factors. Blood pressure was great, diabetes was being controlled, didn't smoke, stopped smoking, exercise to keep the weight down, and so on. Then there was another group of patients in which they were so-so, they controlled some risk factors, but not others. And that's this intermediate group of patients, some treated vascular risk factors. And then there was another group where these guys didn't take care of themselves at all. So the blood pressure was high, the glucose was out of control, they were smoking, and so on. So they looked at the mini mental state, which is kind of the poor man version of a serious neuropsychological testing, for the following 36 months. And what they found was that if you were controlling your risk factors perfectly, you had less chance to kind of drop your mini mental state over the next 3 years. But if you didn't, you had a much rapid decline in many mental states. It's providing evidence that if you take care of your blood vessels, perhaps you can be better in more than one way, Alzheimer's disease or otherwise. So what I've showed you is that the neurovascular unit is essential to maintain the homeostasis of the brain and to make sure the brain does what it's supposed to do, particularly with respect to cognition. And if you have vascular risk factors or hypertension, aging, and Alzheimer, you have neurovascular dysfunction, which is mediated by oxidative stress and inflammation. As a result of that, you have cognitive impairment resulting from failure of the neurovascular unit, which manifests itself with the inability of the brain to function. Thank you.